couple of years is you've seen nuclear fusion, the big record-breaking fusion advances they're making at Lawrence Livermore National Labs. The core piece of that is actually a micro-machined diamond-coated shell. So without silicon micro-machining, they couldn't have broke that record to contain that deuterium and make a tiny little target. So it's used everywhere. And I'm amazed. I keep finding new applications for it that I wasn't even aware of. Diamond is going to be big in power devices because it's a big wide gap semiconductor. Graphene's already been used in memory. That's a similar material. And diamond shells are being used in nuclear fusion. So it's crazy how all these new materials we develop in the IC fabrication research areas are finding other applications, whether it's machine tool hardness, nuclear fusion, quantum technology. It's just going everywhere.
Tell us more about quantum technologies. I mean, quantum computing has been a buzzword for more than 20 years, but every time it looks like a mirage. Having been on the material side, do you see it coming to fruition in the near future?
Yeah, the big problem is decoherence, quantum decoherence. And so how long can you keep these states working? And so the one approach that gets the most publicity, you see all those gold, these gold meshes of wires and tubes coming down. That's to cool down the chips that Google and IBM make to like millikelvin to try to stop the ions from vibrating or the atoms from vibrating in these chips. So they're using extremely low temperature cryogenics to try to overcome the decoherence problem. There's about 20 different ways people are trying to do quantum chips. One of them that I really like is MEMS based. They're doing vacuum sealed wafer bonding with an ion vapor in it. And so they're using this ion vapor, which has electron shells that you can manipulate with magnetic fields or electrostatics or thermally, but to create these different quantum levels. But this thing has to actually be heated up to about 40 to 50 degrees C to get this vapor, this metal vapor to form. There's some really interesting, promising work being done with these micro-machined. They're actually optical. I call them quantum chiplets, because you have the vapor trap in the middle, which is the micro-machine part. You have a semiconductor laser on top, and you have a photonic receiver on the bottom. You're stimulating this optically. It's contained with a micro-machine vapor cavity, and it has to be heated to 40 degrees C. So that has a lot of promise for room temperature applications if they can get over the decoherence issues. So in my opinion, I think the millikelvin cryogenic AI chips are more like the old ENIAC system, the computer that filled up a huge room back in the 1950s. The MEMS approach could actually be a room temperature personal quantum computer chip that could be used for personal AI. If you could do it at room temperature or just a little bit above room temperature, it could be on your watch. So that would be revolutionary.
Nuclear fusion has been a dream again for centuries, and especially after nuclear fission became possible more than 100 years ago. What's your prediction on when will nuclear fusion be commercially viable?
Yeah, it's always 50 years in the future. That's what I've heard my whole career, because I remember as a freshman in college looking at this, because I thought about material science, nuclear engineering, and it's like 50 years in the future. The interesting thing with the National Ignition Facility experiments was they got more energy out than they put into the vacuum chamber. There's 192 lasers that compress this and cause this inertial confinement. However, there was like 300 times more power needed to power those lasers up. When you think of the total system, it just had a gain of 2 or 3 when you just look at the small vacuum chamber where they imploded the nuclear fuel. So I heard one of the scientists say, to do this cost effectively, to generate power, you'd have to do 900,000 ignitions a day. So about 11 or 12 a second. So you think, wow, they can't do that because they're doing one every 6 months right now. I've actually got an article coming out next month in CMM magazine about this. So the analogy I like to draw is coal power. So 2,000 or 3,000 years ago, people were using coal in campfires. So you were throwing one chunk in with the wood and you got some more heat. That's kind of where we're at now. So to become an efficient generator of power, we obviously had to have the Industrial Revolution. So we had to have a lot of stuff in parallel. They had to learn how to not throw shovels into the steam boiler. They had to have a conveyor belt. They had to crush the coal into pellets and just feed it in nonstop. And that took 100 years or so. So you think, okay, 900,000 nuclear micromachine pellets a day is huge. We can make 900,000 ball bearings a day or 900,000 computer chips a day. I thought that was somewhat insurmountable. But then I saw a video about ASML's EUV stepper, their aligner. It's used by TSMC and Intel to make those 5 and 2 nanometer devices. To generate that 13.5 nanometer wavelength, they have to squirt in a little pellet of tin and hit it with 2 lasers to generate that wavelength. And they have to do 50,000 of those a minute or a second. So they're constantly laser ablating these tin pellets to generate the UV. And it's faster than what you have to do to generate the nuclear fusion. I think it's 100 times more frequent. I believe 50,000 a second to generate that constant EUV stream. Well, the point is, ASML has figured out how to laser ablate just a huge stream of these tin pellets. And could Lawrence Livermore National Lab figure out how to do the same thing with these deuterium tritium pellets? Maybe it's going to come faster than we think.
Now you're talking science fiction. Quantum chiplets, micro machine pellets. This is really cool stuff.
CBS 60 Minutes did a video, back in January after the December breakthrough that Lawrence Livermore had. They went to the lab and they talked about all this. They showed the pellets and they said, yeah, we shot one of these pellets and we got more energy out than we put in. The researcher said, but we'd have to do 900,000 of these a day to generate electricity. So that's where I got that number. And then on YouTube, there's something about the ASML EUV stepper, and that's where I got the 50,000 per second tin droplet laser zapping tooling that already exists. It's out there. If you can get clever people to figure out how to merge those two together, maybe in 10 years, you'll have nuclear fusion generating power. And there's a lot of nuclear fusion startups, and they're doing other plasma confinement techniques, but you just never know. If you get enough ideas out there and some venture funding, what could happen?
So, Doug,